We press.
Yeah, I have press recording. Very well. Nikita will speak today about higher dimensional solitons. We already spoke in one previous talk about these two-dimensional solitons in the theory of tropical sandpiles. And now Nikita will speak about his generalization. The paper is out, I believe.
Yeah, it's already published in Arnold's journal.
Excellent.
It's Arnold's journal, or something like that. Well, so let me start with example. So here I have a polytope in R3. And then I intersect this polytope, let's call it, I don't know, well, alpha. I intersect it with a grid, that cube, and h is a small parameter, h tends to 0. Okay, and so here on this set, I have a sandpile. So this will be my graph. And here I put 5 grains everywhere, right? Because like in R3, each vertex has 6 neighbors. And so 5 is the biggest stable state, the maximal stable state. Maximal stable state. And then I add grains somewhere. And then, well, the question is what happens? So here is 5 grains, it's denoted by 5. And then I consider the state 5 plus sum of delta p, where p belongs to a finite collection of points. Points in alpha. And so that's my state phi. And so the question is, what is the relaxation of phi? And the goal is to establish a similar statement that the relaxation of phi is something like a tropical hypersurface. So a claim is that the set of vertices where this is not 5 is approximately a tropical hypersurface. A tropical hypersurface passing through the set P of points. So that's my set P of points. And here again, it's not, but well, it's not yet written. But here it needs some preliminary steps. But on the picture you can see what happens actually, because here my sandpile is something like, so my graph is something like, well, x, y, z bigger or equals than 0. Then we have something like x plus 2y, 2y is less than something, z less than something, and x plus y plus z less than something. Okay, and maybe also like x less than something and y less than something. So basically you take a cube. This cube is like 25 times 25 times 25. Then you also add this plane, this one, and you also cut it by this plane. And that's my polytope alpha. Okay, so it's given by some linear equations. And then I put 5 grains everywhere, and then I add just 1 grain. And here I added 1 grain to just 1 point. So this point is somewhere here, like somewhere inside, somewhere there. And then here you clearly see a tropical hypersurface passing through this point. So here you see the boundary of my polytope, and the tropical surface is inside. Okay, so for example, that's one face of tropical surface. That's another face of tropical surface, and the same further. Then here on the picture, like different colors are presented in different parts. So here 5 is white, Then I think green is 4. Then yellow is 3. Blue is 2. Orange is 1. And red is 0. And so you see that here we clearly see some something like which looks like a tropical hypersurface, which is composed of different parts. And these different parts, they have like different recipes to construct. So you have several colors, and you can for each direction. Let's say for a hyperplane, here you have this composition of like blue and green. For the hyperplane in this direction, it's like yellow plus green plus blue, which is here. Okay, and you see some red only along the edges, right? So here the tropical surface is something two-dimensional. It has faces and edges, and all of them are periodic. And so the goal is to construct such objects. And it's given as follows. So here I give you a theorem. Here it's theorem. So let's suppose that we have a polytope delta. It's a polytope in Rn, well, in Zn, such that the convex hull delta intersect Zn consists only in vertices of delta. Right, so it's kind of a polytope without lattice points inside, without lattice points on the edges, faces, and so on. So only vertices. And then we consider a function like f is a function which is minimum of p times x plus qp, where here p belongs to a polytope. It's the vertices of this polytope. X is a point in Rn, and qp are constants. Okay, so basically you consider the tropical function which corresponds to this polytope with arbitrary constants here. So it's arbitrary constants. And then again you define some smoothing procedure, like Misha explained, that you define functions, superharmonic functions, which coincide with f near the deviation locus of f. The Laplacian of f is not 0. So in a finite neighborhood. And then there is a minimal point was minimum of this function. And then the claim that if we say that this point was minimum is theta of f, then all the patterns appearing in the above sandpiles are like 2n plus 1, 2n minus 1 is the maximal stable state, plus the Laplacian of such function theta of f. So here it's a theorem, and here it's why do we need this theorem? Why do we need this theorem? Okay, any questions so far?
So, but they are, sorry, go ahead, Semester.
No. Just to follow this is exactly the same. Well, one of the versions of the theorem in dimension 2, isn't it? It's just
exactly.
exactly.
But in dimension 2, you have So let's say, so what happens in dimension 2? So for delta, you have several possibilities. So delta can be just interval, like interval without the lattice points inside. It can be triangle without lattice points inside, or it can be a parallelogram without lattice points inside. Okay, so in case of dimension 2, we just need to consider all these three cases. And here, you see, so here my polytope is in dimension n, and we have much more possibilities. So it can be interval, it can be triangle, it can be something 3-dimensional, 4-dimensional, and so on, any dimensions.
No, yeah.
It's exactly the same.
Yeah. Misha?
No, just one question. So we still call them solitons because they behave on the waves in a predictable way, right?
Yeah, so let me also explain this moment. Because so here, what is a soliton? A soliton, it's what we obtain if delta is an interval. So when you have this Zn, and when you have 2 points, just such that here there are no lattice points, then your function f of x is just the minimum, let's say, of 0 and p times x plus some constant, okay? So it looks like, just minimum of 2 functions. And when we do this procedure, when we prove that there is a point as minimum, it looks as follows. So we have some function which is the same here, but here in between is something like something here. It changes. And then the state, which is 2n minus 1 plus delta of this function theta f, so this is theta f, is a soliton. So in the following sense, that if we apply a wave operation, so we apply a wave from a point, let's say z, to the state, it will be the same, but here you have Laplacian of theta of f, let's say, here you change f. So for example, if your point z belongs to the points where the minimum is attained at 0, then here you have, well, f prime, which is the minimum of 1 and px plus c, and here you have f prime. So exactly what happens is you just, change the coordinates. You move your soliton by 1. And if you apply the wave operation from the part where the px plus c is minimal, then you add just 1 to this px plus c. And, well, yes, so that's the solitons. And also one can prove that if you have a state which gets translated by some vector when you apply a wave, and then they are all classified by intervals without integer points inside. So solitons, it's when delta is an interval.
Now, let me ask, when these things were called solitons, they were inspired by some solutions of some PDEs that get discretized or something like that.
No. We call them solitons because they look like waves on the water. Like, when you have water and it's a shallow water, it's like, it's shallow. And then you can observe that waves, they go like in these piecewise linear directions.
Yeah.
And then they move like, exactly this way. So these waves, actually on shallow water, these are solutions of some PDE, but we have just the same pictures. And
That's right. That's right. But my impression is that this connection, while maybe not work out mathematically, is still true. That there is a PDE and then maybe a discretization or a limit or something.
well,
And
we
then,
failed to do that. As far as I know, there is an article of Sportiello, Paletti, or maybe just Sportiello, which is called Sandpiles as a hydrodynamic limit. And there they have a very close model which produce pictures which looks like a smoothing of sandpiles. But I was not able to understand what's going on. And well, so maybe we just need to try to reproduce their results to see how it actually works.
that's right. But I was just going to ask a new question, so to speak. Because these intervals must correspond to these peculiar differential equations that admit solitons, integrable systems, so to speak. It is a very intriguing question to ask. In the world of differential equations, what are the objects that are not intervals but convex bodies that have no integer points?
Yeah, I understand. So for solitons, they also have some laws of preservation. And indeed, for every soliton, like in physics, you have this orthogonal direction, and you know what happens when some solitons meet. But I'm not sure that the same works in high dimensions. So solitons, as far as I know, they appeared only on shallow water because there are no space solitons. At least, well.
Well, in the string theory, there is space solitons called the brains.
Well, yes, but I'm not sure about whether they have some balancing conditions and so on. So, or for the shallow water, indeed. So you can assign some vector to that direction, and if three solitons meet together, then the sum of the vectors is zero. So whether it's true for high dimensional solitons, I don't know.
I don't know. Of course, I don't know. But I do believe that the question can be formulated and the answer will be extremely interesting. And it has to do with these higher brains. You know, the PQ brains in string theory were just the classical curves. And I think the higher brains in string theory in the same limit will be these D brains or whatever will be related to your theory. So
yeah, yes, it's very, very interesting.
it is just a question that at some point someone should ask, you know, and think a little bit. Very nice.
Yeah, and also what happens when two solitons meet together? So in my setup, so you have one interval for one soliton, you have another interval for another soliton, and then you just connect this triangle. And if this triangle is without integer point inside, then you know what happens with solitons. So you have this hyperplane soliton here, hyperplane soliton here, and they meet and they go here, orthogonal to this third vector. So that happens when when two solitons meet together. When you have three solitons, again, you just draw these intervals, three solitons, and then you connect this like a pyramid. And if this pyramid has no lattice points inside, then you know what happens. So basically, you have this like one soliton, another soliton, and then they go like a tropical surface.
Fascinating. And what if they have interpoints and we do further subdivision? Can we tell something?
Well, if they have some integer point inside, they must somehow separate. So you have more like a bigger dimension of solitons. So for example, when you on a plane, so if you have one soliton like that and one soliton like that, and even this triangle, which is dual to this picture, you have integer points, then the picture should somehow split. So here instead of this, you have some domains inside. So first you have to split one soliton in two, you have to split another soliton in two, and then they meet like that. So that's what happens.
So it is solving the problem of resolution of singularities, or what is it doing?
Yeah, exactly. So basically, what happens is that when you have three solitons here, you should think as a minimum of three functions, three linear functions. So, and when you have this new phase appearing here, it means that you can, this picture will be the minimum of the three linear functions plus one more linear function. Linear function corresponding to this lattice point inside. So here you have this triangle, and if you have some integer point inside, then this phase corresponds to this integer point inside. So for each integer point inside of your polytope, you have this one-dimensional deformation of these new phases. And indeed, when you resolve singularities, you also basically count lattice points inside your polytope. So yes.
Yeah, that's right. Very nice.
Okay. So that was the formulation of the theorem. So I stated. So again, so we have this polytope without lattice points inside. I have a function which is a point, just minimum of some linear functions, one linear function for each vertex, and then I claim that there is pointwise minimal superharmonic function which coincide with my function f in a finite neighborhood of the set where it's not harmonic. Okay, so how it works? How the proof works? Proof works by induction. So first of all, we need to prove this statement for intervals. So proof. So the first step is when delta is an interval. So in this case, my function f is just minimum of two functions. Let's say 0 and p times x plus constant. And then I consider the lattice such that p times l is 0. Okay, just consider the orthogonal lattice to my vector p. And then it means that f is periodic with respect to L. Just by definition, right? Because if I add to X any vector orthogonal to P, the value of F does not change. So it means that instead of Z power N, I go to Z power N factor by L. So nothing changes because all these procedures of like taking point as minimum and so on, they all can be made periodic. And then it looks like we have a cylinder. And then I know that somewhere here my function is 0. Here my function f is px plus c. And then I have this procedure of like diminishing and diminishing my function f. So here I claim that there is a point plus minimum. And it's like similarly like in two-dimensional case with Misha, one can prove that one can smooth this function by like subtracting 1. So here I call this process husking. It's the same as smoothing, but it's husking procedure. So instead of function f, we define s1 f, s2 f, and so on. And you have the property that si f minus si plus 1 f is at most 1. So each time you diminish your function by at most 1. And then you look at the points, look at the set skf, the Laplacian is not 0. Okay, so initially this set is exactly just the the set where my function has a slope, the corner. So my function, it has non-smooth locus as a plane, and when I pass to the cylinder, it has just this image of the plane here. And then when I go to like sk of f, it gets somehow distributed, so it gets bigger and bigger. But thanks to that it's a cylinder, it's always contained in a, it's always finite. The sum of this, this set is at most some constant. And so if this process is infinite, so I have like some k very, very, very big, then it gets very, very distributed among this, my cylinder. And then somewhere inside, I have a huge part where my sk is harmonic. And then in this part, sk is linear in this part. Right, again, that's a similar statement that this sk is sk of f is bounded by some linear function. And so if you have a harmonic function which is bounded by a linear function, then itself it's linear. But then it should correspond to some integer point, to some lattice point. In my polytope delta. But there is no such points. Therefore, the process cannot be infinite. The process is finite. So it means that there is a point plus minimum. Okay. Are there any questions about this part? So that's exactly the same as on the plane, and maybe Misha explained it.
Very nice proof. Yeah. It's yeah, the emphasis of the proof is slightly different, but it's very nice.
Misha, is it okay?
Yes, it's totally okay. So yeah, so I actually didn't explain it in these details. So I spoke about the cylinder, but yeah, I didn't pronounce explicitly this argument.
Okay. So anyway, so here the argument is exactly in 2 dimensions, because in 2 dimensions you have a cylinder like on a plane, like 1-dimensional vertical and 1-dimensional horizontal. But in the case of Zn, you have the same. You have 1-dimensional vertical in like some finite number of dimensions here, but it doesn't matter. In fact, it's just the same.
Very nice.
Okay, the second part is when delta is a triangle. And here again, in fact, the proof again is the same as on the plane. So here it means that f is just the minimum of 0, some px plus c, 2x plus c prime. And then you take L, which is orthogonal to the space generated by P and Q. And then again, you factorize by this L. And again, so your picture looks like 2-dimensional essentially, because here in this factor, again, you have just 2 coordinates, which can be infinite, and all the other coordinates are kind of finite. So it looks like a flattened plane. So it's kind of, not a cylinder, but it's kind of plane. It's infinite in 2 dimensions, but finite in 2 other dimensions. And here, then you say that you know what happens when you take this Haskin of these 2 functions, and these 2 functions. And so your picture like this follows. So you know that here we have this like 3 solitons, which corresponds to this procedure which I just explained for the sides of my triangle. So for each side I do it. And then I just need to prove that when I again try to make less this function, try to Hask this new function, again, I look at this deviation locus where my function is harmonic, and it gets something here. So it looks like a tropical curve, and then here you change it only here. And then again, you just control the number of points where the Laplacian is not zero, and you show that if you can do it like for many steps, then somewhere inside you have this locus of linearity, linear part. And again, it contradicts to the fact that my triangle D, the delta is without lattice points. So proof goes exactly like that, but here we need one more complication. Because the main step is as follows. So the main step of my procedure is when I try to diminish my function by 1. And so like I have function f, and then I pass to S1f, meaning that I try to find function such that it's less than f. The difference is at most 1, but function S1 of f is still superharmonic. And here possibly what can happen is follows. So maybe, so that's my function. So that's my set of like df is not 0. That's the set is somewhere here, somewhere here, somewhere here. So maybe it is possible to diminish my function S1f such that it changes all along these edges very far from the from this vertex. But one can prove it's not possible, because the picture along this edge is periodic. Okay, and here, if somehow this S1 of f changes like very far from the tropical vertex, it means that somewhere here you can find two identical parts which change like similarly. And then it would mean that I could find some function which is less than this function corresponding to this edge, which contradicts to my first step. Because you remember, for the first step, I found that there is some point mass minimum corresponding to these edges of my tropical curves, all these hyperfaces. So it's not possible. So this difference between S1 of f and f, it cannot prolong very long from the tropical vertex. So it means that each time I pass through f to S1 of f to S2 of f and so on, I change only in the finite neighborhood of this of the tropical vertex. So I cannot change my function far from the previous step. And then all the argument works. Is it okay?
Very
Yes.
nice, yeah.
Okay, so and the next step, what happens in higher dimensions? So let me explain just the step like when n equals 3. So here I have a polytope in R3. And here the first, what I do is the same. So I have my function f. Again, now it's a minimum of 4 functions. And then I take this pointwise minimum for all edges. I can do it. And then I take this pointwise minimum for all faces. So what happens is that I have this point, and I know that along the faces I have some patterns, and along these edges I have some patterns. And now still I try to decrease my function and go from like f to S1 of f to S2 of f and so on. And what can happen here? Just look at the set where f is not S1 of f. So it can be some set like that. So it goes somewhere along this tropical vertex. And here I have to prove that it cannot go far inside the faces, right? Because it cannot go far along the edges because again, just cut it because it's periodic and find two identical pieces because there are only finite number of possibilities for them and arrive to a contradiction. But if I go like inside this faces, so here it's not clear what to do. But here again, some more fine version of this argument works. So because here, if I have this, let me just draw this picture. Yeah, it's here. So that's a picture of this tropical vertex. And so here is the image where how the set f is not equal to S1 of f can look like. And my first claim is that this set cannot go far like here, inside the faces. Why is that? Because each face here is also periodic in some dimensions, right? So it can be cut into identical pieces. And then you do the following. So you look at some piece which is far from the tropical vertex. You look at its neighbors. Then you look at neighbors of these neighbors. And if at some moment you stop getting new patterns, so you just look at the restrictions of this S1 of f to this like primitive parts. If at some moment you don't get anything new, then you can take just point was minimum of all these patches, and this point was minimum will be a function which contradicts the minimality of the function corresponding to this face. So it's not just you take some periodic things and take the two identical things of them. So here it's not possible. You cannot find something and then just find a contradiction. So here you need to like give just a bit more fine argument. But still, it took like maybe 1 year to invent it. Again, so I look at the restrictions of S1 of f into these small parts here, and I look at the one layers and then neighbors, and if at some point I stop receiving some new restrictions, which definitely is the case because the number of restrictions is finite, then I take just the point as minimum of all these restrictions. They can be like glued all another, in one pattern, and this will contradict to the minimality of the pattern for this phase. And so this my set of f is not equal to S1 of f cannot go far into these phases. If it's not going far to these phases, then it looks like it going maybe just along the edges, like that. But here again, I apply the same argument. I just cut them periodically. And again, so if it just like in 3 dimensions, then here I find 2 identical ones. If it going to like very far, and construct a pattern contradicting the minimality for this edge. And if it's of low dimensions, I apply my induction step. And so it means that when I consider this f not equal to S1 of f, it always lives in some finite neighborhood of my tropical vertex. So it means the following picture. So that's my tropical vertex, and that was my function f. Then I go to S1 of f, and it changes only a finite neighborhood of this vertex. Then I go to S2 of f, and again by the same arguments, it changes only a gain of this neighborhood plus c. So each step, I just go maybe at most by c. And then it allows me to understand how many points with df is not 0 I have in this set. So after n steps, I still live in some ball of radius Cn with 0. And then I know that since the number of vertices which are not harmonic is like, again, some linear, then somewhere inside I must have a part where my function is linear. And since my function is linear, it should correspond to some point in my polytope. But there are no lattice points in my polytope. And so it means that this process must stop at some moment. And actually for small slopes, it stops almost immediately. So you see, so here, for example, somewhere here you have this vertex corresponding to this meeting of 1 soliton, 2nd soliton, 3rd soliton, and 4th solitons. And so you see this like vertex is very, very small. So maybe it means that this process of husking stops maybe like on the 2nd step, maybe 3rd step. So not much steps. Okay, so that's it. That's what I wanted to tell you about truth.
Fantastic. Beautiful arguments.